Follow again.
Start now. Oh.
Okay, so next and last speaker for the session today is James Weber from Panasonic, who will be presenting technology for dicing wafers based on plasma.
Thank you. So thank you very much for the invitation again today. It's my pleasure to present and to talk with you all the last 2 days. So I'm from Panasonic, probably most famous for televisions and washing machines, but I'm not here to talk to you about that. I will show this brand video first, and then after that, can take it from there.
A better life, a better world.
So that's, don't start. Close. So that's a good demonstration of all the different things that Panasonic is doing, many, many different things. We are one of those divisions towards the last third of the video, the industrial side. So Panasonic is manufacturing equipment and for use in manufacturing, and one of those is plasma dicing. I will talk about that today. So it's I will tell you about what it is, the features of plasma dicing and how it can be applied, the specific details of how we do it, and lastly about our demonstration center in Osaka. So the conventional way of dicing has been with blade and still is with blade. But as you can see on the left, there's a good evidence of the damage it can cause. A new approach on the right is existing dry etching technique, but applied in a practical way on dicing frame with a mask on the wafer, where then you develop the mask or use some other techniques to remove the mask where you want to dice, and where there's no mask, it will be etched. So instead of a line-by-line mechanical process, you can now think about a whole wafer-based process that is applied on the whole wafer. So again, if we line the existing techniques up with each other, we have blade and laser dicing. As you can see, line by line. So the first thing you can think is as the devices get smaller, the length of time to dice the whole wafer will increase. That doesn't get affected by, it doesn't affect plasma dicing because the mask is existing on the whole wafer. The only thing that's affecting the dicing time is the thickness and the material of the wafer. So what are the issues existing at the moment? You can see in the top right, chipping again, caused by mechanical action. As in the bottom right, as devices become smaller, the process time increases because basically you need to just cut longer. And as the devices get smaller, maybe the devices start to get the same size as the blade thickness, so you're wasting wafer space. Plasma dicing can address all of those concerns. Again, you can see on the left the damage in more detail caused by blade dicing, but plasma dicing on the right, completely damage-free. And if we go back to my example of wasting space, you can really increase yield with plasma dicing. On the left, you can see the thickness of the dicing street. I'm sorry, there's a spelling mistake in here. I should have fixed it. It's kerf, not kurv. The blade thickness is quite thick, but Panasonic plasma dicing can offer down to 10 or even 5 micrometer street width. So if we take this example in the table on a 12-inch wafer with a relatively small device of 0.4 millimeter, you can increase yield by 30%. And because it's a mask-based process, you're no longer limited by a standard grid shape, so you can start to think about variant shapes or offsets if the devices are relatively large, and you can also include multiple sizes on the same wafer. Anything is possible, basically. For the basic case of silicon, etching speed is around 25 micrometers per minute. And if the wafer is exceptionally thin, the initial dicing speed can be up to 30 micrometers per minute. So again, if we look at the damage caused by blade dicing and by blade dicing on the left, you can see the chipping and the damage-free evidence on the right from plasma dicing. But why is this really important? Well, if you take the chips and perform a bending test on them, you can see that plasma diced chips in blue are much stronger. Basically, if you perform this test, the blade diced chips will just crack due to the micro cracks inside the device and separate quite neatly, as you can see at the bottom. But if you try to perform this with plasma-diced chips, they fracture in the same way that silicon would. So this is our machine in the single chamber configuration. It's the APX300. It's including the load lock chamber at the front where the wafer cassette is loaded in, and then in the back is the plasma chamber. And then it's possible also to take the same common single unit in purple and arrange in either a single, double or triple configuration for mass production. So if we take a deeper look inside the machine, we'll go into a little bit more detail in the next slides. So our plasma source is an enhanced ICP. We have integrated endpoint monitoring, so the machine can tell the different layers of the wafer, and also importantly, once the dicing is stopped, or once the wafer has finished being diced, then dicing should stop. Recipe, it's possible to program the machine to handle multiple recipes for different wafers, or also from cassette to cassette. We can offer fluorine-based gas or chlorine-based gas etching. And typically, most of the time, we're using the wash process to etch. Again, this is a detailed look inside the machine with a schematic. We have our multi-spiral coil ICP. The main point to take away from here is that it's a very high density plasma, and uniformity is one of our #1 concerns. So if you have a 6-inch or a 12-inch wafer, whatever's happening in the center of the wafer is also happening on the edge of the wafer. So I always say, I don't think about yield on the wafer. It's either not 100% or 100%. During the initial phase, we have to develop the recipe. But once that's established, you should be looking at 100% yield, because the dicing will occur over the whole wafer uniformly. So because we dice on a conventional dicing frame and tape, we need to make sure that the temperature is controlled so that we don't see any tape melt, like in the top right. Basically, we never see that thanks to our design. Two aspects. So underneath we have electrostatic chuck, which is cooled to maintain 50 degrees Celsius dicing temperature, and also our patented covering design. So it's designed to the same size as the wafer, so that only the wafer is exposed to plasma, and this shields the edge of the dicing tape and frame. So taking a little more detailed look at the processing capabilities from a silicon point of view, so dicing speed can be around 30 or up to 35 micrometers per minute. Uniformity on the wafer itself is less than plus minus 3%, and also wafer to wafer at the same level. So then we also have different selectivities available, whether you use a photoresist or a hard mask. Then here are some examples of different dicing speeds if there's different layers in the wafer. So sometimes half a micrometer per minute. Gallium arsenide, I think, is also important for today. We're using chlorine-based gas around 5 micrometers per minute. And then these are some examples of the different situations we've diced in the past. So it's not always so easy for us to just get a silicon wafer and with nice, relatively wide dicing street, like 10 micrometers. Customers are always pushing us to do a more difficult application. So you can see a relatively large aspect ratio here, only 5 micrometer wide street width, but 175 micrometer depth. Also side by side here, but very thick is also possible for us. And multiple layers on the bottom right. Gallium arsenide also getting more common for us now in Europe. And if it's a 3-dimensional wafer as well, no problem for us to handle. We're also able to dice stacked wafers. And SOI wafer is also getting more common for us to dice. So we have experience with these globally. And I will show in another slide, but we also have the ability to dice with die-attach film. This is some more examples of our capabilities, able to etch vias. This is our dry etching machine, so it's the same machine, but used just the bare wafer instead of being on the dicing frame and tape. But this is our plasma dicer on the end. We are also able to dice gallium arsenide wafers with faster than 4.4 micrometers per minute dicing speed and less than plus minus 2% uniformity on the whole wafer. So, of course, we know the industry trend in going in all these directions now. Everything is becoming more thin, more brittle, and smaller. So we also need to think about our target market. Blade dicing is existing for many years and will continue to exist for many years, basically because it's cheap and it's easy and it's established. But it's all more of an economics question. As the device gets thinner and the chip size reduces, it starts to get very attractive for plasma dicing, considering those issues that I talked before about increased yield and more devices or a longer dicing time because of the more devices on the wafer. So in different areas of the industry where advantages can be gained from plasma dicing, you can increase the yield by reducing, for example, from 60 down to 10 micrometers street width. Much faster dicing time because the dicing is performed on the whole wafer, and it's based on the thickness of the wafer now, not the amount of lines that need to be cut. It's particle-free, and it's very important, especially for image sensors. And damage-free, so as I showed you before, the increased strength due to no internal cracking. So there's two ways that we achieve this plasma dicing process. Either we perform a photolithography masking method, or we can do it with laser patterning. So important to note, the laser is not etching or cutting the wafer, it's merely making a pattern on top of the wafer in the same kind of principle as photolithography. But laser patterning has the added benefit, if you have a metal layer, you're able to also etch this out. So if there's metal in the top layer, this plasma cannot etch that. So for photolithography, we either apply that with a spin coating on ring frame or spray coating. I'll show some examples of that at the end of my presentation. And then this is the alternative with laser patterning. One of the possibilities is a tape from Furukawa company in Japan, which combines backgrounding tape and a mask layer in the same tape. So as you can see, I will show a video about it, but there's when you remove the backgrounding tape, it leaves this yellow mask layer, which is then patterned, and then after that it's the same principle as a photolithography mask. Where there's no mask, it would be etched. This is just don't worry, you don't need to read it, but it's just an example of our industry collaboration. So Panasonic is providing the etching machines, but alone we cannot achieve much. So that's why we have well-established relationships globally with big companies like EV Group or SÜSS for the lithography side of things. Also gas and tape manufacturers or gas supplier. This is laser patterning provider that we partner with, Furukawa, for the combined tape. So these are not specifically products from Panasonic, but we work with these companies to enable good collaboration. And usually our customers already have these products in their fab, so we have to also work with that. So I'll show you a few quick videos on the concept. This is the basic concept of how plasma dicing works using a photolithography approach. So first, the wafer should be background or grinded to as thin as possible, because if the wafer is thinner, it would dice faster. So then we put the thinned wafer onto a dicing frame and tape, and then delaminate the backgrounding tape. Then we spin or spray coat photoresist onto the wafer. And then we need to develop this out. So now you have a patterned wafer on dicing frame and tape. You put it inside the dicing chamber with the appropriate recipe and dice through the wafer down to the dicing tape. And then rinse or ash. In this case, it's a water-based resist, so it's quite simple, but you can also use O2 plasma inside the dicing chamber to remove this photoresist. And now you have a conventional dicing frame and tape with a singulated wafer. That's the basic concept. So this is just a schematic of all those steps again. There's the added step, which is not in the video, of a stress relief step. And this also highlighting that you can use O2 plasma to ash the resist off. And if it's not possible to etch from the top of the device, the wafer can basically be flipped, and the same approach can be performed from the backside. So this is the alternative approach with laser patterning. So there's a few approaches available. This is the same concept as I just discussed, so putting a water-based resist on the top using a spray or spin coating, but also we can use this Furukawa tape. So I'll show a couple of videos just quickly to highlight that. So this is the Furukawa tape. It's kind of a nice combined approach. So you can see the different layers in this backgrounding tape. And you'll also notice the metal layer now. So first we background the wafer again. Thinner is better because it's quicker dicing time. Then we put that wafer onto conventional dicing frame and tape and remove the backgrounding tape, but exposing this mask layer. That is then patterned with the laser, and then alternatively you can etch the metal, and then same as before, put it inside the plasma dicer, etch through the wafer until the dicing tape, and then ash off the tape. So I'll just show you one more. It's the last one, but it's highlighting the easier step of using the water-based resist or pattern. So in this case, we have to spin or spray coat the water-based resist on top. Sorry. Again, dicing through the etching through the metal, and then put it inside the plasma chamber. But the difference with this one is it's water-based, so relatively easy. Just wash it off and take any debris with you as well. One integrated step based on our experience with plasma cleaning in another division. It's a patented Panasonic process. So this is what it looks like after the laser patterning has been performed. This is just a mask, so it doesn't matter. What's more important is the edge quality here, because if it's exposed like this, it will etch vertically down. And make a rather undulating side quality. But if you run our plasma cleaning step inside the same chamber, it cleans things up nicely. And then this is just an example of us being able to dice with die-attach film. So if we take the same chips and perform the same breaking strength tests, this is the chips that are patterned with laser. You can see that there's no noticeable drop in strength compared to the previous photolithography test. And yeah, this is just the last section of the process. We wanted to test what we talk about. So this is a kind of test wafer that we received. We wanted to set our target to prove that if we do a photolithography method, we can conformally coat 10 micrometers all the way around. And then we can dice using laser patterning with 30 micrometers street width and lithography of 10 micrometers. So this is getting a little bit old. It's about 1 year. So we've beaten this. We're down to 20 and 5, even lower. But whether it's realistic or not, I'm not sure. But we can do it. We can at least dice it, etch it. So this was the example of conformal coating with the help of EVG. We were able to achieve 12 micrometers conformally coating all the way around the device in all areas, especially critical areas like here, and no wastage in this region. And yes, opening with 10 micrometers, no problem, and etching it, no problem. And same with laser. We can at least do 30, but as I said, smaller is also possible. So finally, if customers have their wafers and they want to investigate plasma dicing, we have to demonstrate it for them. In the past, we used to just offer the dicing service, but it's not so realistic because a whole bunch of other steps need to be performed before we can dice. So backgrinding and photolithography, it means getting the wafers in another country, Japan in this case, sending it to another vendor. You have NDA issues, logistics costs, all this time, all these problems. So we decided this is not practical. So we opened our own demonstration center in Osaka. So around 3 years or more, sorry, 3.5 years or 3 years and a couple of months in Osaka. We have our two different machines. We have our 8-inch dicing frame machine and our 12-inch dicing frame machine. We also have laser patterning machine, backgrinder, photolithography in the back, and then here a whole bunch of analysis equipment. So it's a one-stop shop. The customer can send us the wafer, and we dice it and then analyze it. This is a lineup of all the equipment that we have. And this is the last slide. Just want to highlight that Panasonic is making the machines, the dicing machines, but without integration throughout the whole industry, we cannot integrate our products with their customers. So that's why we like to consider the total solution approach, working with material vendors, integrating with customers' process, and providing our equipment. So that's the end of my presentation, and thank you very much. Relatively on time for lunch.
Thank you, James, for your nice talk.
Thank you.
Well, now it's time for questions. It's working. Okay. Questions? Yeah.
So somewhere in the first third of your presentation, you showed that there's a difference between the way, if you stress test your chips, the way that they fracture, and that you show that when you just dice them with a blade. Dice them with plasma, they fracture very irregularly. Why is that desirable?
No, it's just to prove how strong they are. If you try to do this breaking test, they don't break very easily because there's no propagation of these small cracks. They literally shatter like silicon. So yeah, from an optical point of view in the presentation, it looks worse, but that won't happen in your pocket, for example, when you sit on your bank card, or if you do these kind of stressful environments, it doesn't just break. It can actually handle, it does have the similar strength to silicon. That's the point we want to
It can handle a lot more stress, you mean?
Yeah.
Yes, okay, no,
Yeah,
thank you.
Thank you. Any other question? Yeah.
Thank you very much for the nice presentation.
Thank you.
I have a question. You started with a nice comparison, so comparing your technique with the standard saw. Can you comment, for instance, what would be the advantage versus another techniques like stealth dicing?
The advantage of plasma dicing against stealth? Yes, well, for example, you don't have this heat affected zone, and from my understanding with stealth dicing, there's also quite a lot of cracking. So with plasma dicing, you don't have any of that because it's etching in these steps all the way through. Yeah, that's important for several reasons. I think it can have advantages because there's no cracking or heat area, you can extend the active area on your chip or bring the dicing street closer to the chip. You don't have to leave this kind of a buffer area. Also, we have some customers in Europe who are working in space or subatomic particle detection or medical, and they need a very perfect sidewall because I don't know the exact details, but I'm sure there's some physicists in here who know much better. But yeah, if the sidewall is much better and flatter, you don't have these leakages, dark currents, and all these kind of things. So that's been mainly the two areas that our customers are interested in.
Thank you.
Just so I can make one more comment before we finish. I often hear from fabs when I talk to them, well, that's a great technology, but we don't want to look at it yet because our customers are not demanding it. But then if I speak directly to the customer usually says, well, we only can use what the fab has. So I'm stuck in a loop. So all I can say is, if you like the concept here, please get in touch with me, and then I can try to facilitate these kind of discussion. But I think without driving from the customers, yeah, of course, industry will not update so easily because everything is running more or less fine. They will leave it, but I'm willing to support however I can.
Okay.
Thank you very much.
Thank you. Okay, so, well, this was the last talk for the event this year. Thank you very much. So we wish to thank all the sponsors, exhibitors, and of course the speakers which make this event true. I also like to thank all the colleagues that have attended to the event. So now we will have a closing standing lunch, and perhaps there are some business-to-business meetings still to run. And with that, I wish to thank you all of you again, and perhaps see you next year.